Welcome everybody to Dude, Where's My Tweet? Taming the Twitter Firehose. I'm Andrew Noonan. I'm a software engineer with Gnip. I'm controlling two laptops, so bear with me. So first I'll get into who I am and what I'm going to talk about today. My name's Andrew Noonan. I'm a software engineer at Gnip. Talk a little bit about who Gnip is, what we do, kind of what our business model is, and how Cassandra fits into all that. Talk about how Cassandra and Gnip first got together, what it was we used it to solve, a little bit about rainbows and unicorns, and hopefully some time for questions at the end of it all. So who is Gnip? Well, Gnip is ping spelled backwards. That has a lot to do with how the company started. We tried to reverse the pinging of social media APIs. We provide a centralized streaming HTTP connection for social media APIs. We are in beautiful Boulder, Colorado. It's a pretty awesome place with a lot of technical companies around. So that was a big thing in helping us when we first got into Cassandra, to lean on those people, talk to them about their experiences with Cassandra, and hopefully try to avoid some of the same pitfalls that they had. So we are like I said, a social media data provider. So we front all the large social media publishers. Big one, as you'll know, is Twitter. But we also have Tumblr, WordPress, Discuss, Intense Debate, list goes on. You can see them up here. So all these different publishers provide us with a unique problem. So Twitter is a large publisher in terms of the number of activities that we see, but each new publisher we bring on might have a different format, large payloads that we have to deal with. So there's a lot of variability in the scale that we deal with, and social media publishers are only growing, social networks are only growing, so we as a business have a large need for scalable solutions. So speaking to Twitter specifically, the Twitter Firehose as it stands today is like 5,000 to 7,000 tweets a second on average. We regularly see spikes of up to 20,000 tweets a second. This right here is a spike we saw recently that was like up to, I think it was like 15,000 messages a second, completely unplanned. We didn't know it was coming. Twitter just gets customer queues or user queues backed up somewhere in their system. All of a sudden they flush, and we see some downstream event that we need to have our systems planned in order to handle these events smoothly, not drop any messages. There's planned events that we see all the time. Michael Jackson's death, not very planned, but it's a social media event. We see the Super Bowl, for instance, last year was like 20,000 messages a second sustained for several minutes. So definitely have to build these scalable solutions that can handle all that. We hold the entire Twitter archive in S3 actually, and we save all these messages as they come into S3. We ingest something like 2 terabytes of data a day. I think we have a full petabyte at this point up in S3. We've got a mix of cloud and dedicated hardware. So cloud's a great solution for these scalable apps that we're writing, but every now and then you need a little more horsepower out of your single machine. So we've actually made some investments in that area. We serve over 95% of Fortune 500 companies with social data. So these are enterprise customers paying a lot of money for this data. They need reliability, they need availability, and they don't really tolerate systems going down, that kind of thing. And speaking to our scale some more, we deliver 120 billion social activities every month, just growing every day. So why all this matters? This matters because obviously tons of data. So everybody here is probably familiar with the idea of big data and dealing with things at scale. We also require redundancy and reliability. So our customers are paying quite a lot of money for this. They've got big dollars riding on it, and so they require a reliable solution that has redundancy behind it. There's always going to be failures, so we build redundancy and reliability into everything we look into. Obviously, that relates to Cassandra, and availability is very important to us. As we encounter real-time problems, we need available apps. So we began searching for different solutions to our data problems, and we were looking at Cassandra. I was on the team tasked to kind of come up with a new technology that we were going to use that was going to be scalable, meet all these requirements. And so I will tell you about how Gnip and Cassandra first met. We had a current system in place that was basically a metadata lookup of historical activities as they left the Gnip system upon customer requests. And this system was seeing a regular sustained write throughput of about 500 to 700 messages a second. And we were starting to see regular spikes up to 1,500 messages a second. And we were building a new product to put on top of this that was probably going to, well, it was definitely going to increase the read requirements on the system. We were thinking about 250 clients at any given time. That has now scaled to more like 500 clients. So it was very clear to us that the solution we had in place right then, which was not a scalable solution, wasn't going to work in the long term. We needed to come up with something else. These were the specs that we were looking at. This is actually a graph from back then, and just for instance, we saw this random spike of 3,300 messages a second. We actually didn't know what the hell was going on upstream at the time. We talked to the publisher and finally found out that they were doing a concerted effort upstream that was batch processes that were causing these increased messages to come down every now and then. So, and they told us that was only going to keep growing. And so we were like, all right, shit, we should probably do something about this. So enter Cassandra. Cassandra obviously seems to fit a lot of the things I've been talking about. Definitely has a high write throughput. So as we were going to continue to see growing volumes in both this first instance where we were really just entering metadata, it'd be great if later we were just shoving all activities we were seeing into Cassandra. So higher write throughput was definitely covered. Definitely a scalable solution. So as we grew out this new product that was going to be throwing a big read load onto the system, we would be able to scale out as we saw more customers come onto that. So that was definitely a check for us. It's highly available. So as we see different network blips, which regularly happen in between our own nodes and our customers and our system, we would be able to stay available to serve any requests coming in. And it was persistent, which is very important to us. We hold historical records of social activities, and it's very important that we persist those, because if we don't persist them, no one else really is. We can't really get them back. It's very hard for us to go back to publishers and say, hey, we were down for a little bit, can we get that back again? But that regularly happens with our customers. They get disconnected from a real-time stream, and they want that data back. They come back to us and they say, hey, can we get it back? And we're in that position to say, yeah, you can. You're going to have to pay us for it, though. So Cassandra, it's rainbows and unicorns. It was, fit these specifications perfectly. It's a brand new technology that was everything that we wanted it to be. We stood it up and we started with, I think, like 2 nodes maybe in AWS. I set it up locally first, tested it, seemed cool. I was like, yeah, let's do it. And put it in AWS, had 2 nodes, started writing to it. The write throughput was pretty cool, but figured we should grow it to 4 nodes, put it as 4 nodes, and we wrote a little test app. We were throwing as much mock data as we could at it. It seemed to be doing great, and so we were like, hell yeah, we figured it out. It's gonna work, right? Well, no, it's not. It doesn't, it's not always going to be the shiny new toy that you think it is. And we learned that fairly quickly. It's to be expected. It's a new technology, it's open source. It's young, it's growing, it's immature, and you kind of have to expect to hit these road bumps, and you gotta really learn what you're doing and pay attention to it. Don't just trust that it's going to solve all of your problems. So let's talk about the road bumps that we did see. So first we stood it up, like I said, I did some initial testing. It was mostly with mock data, some apps that we just kind of wrote up to test Cassandra. But then we actually threw it into our real system, first in staging, obviously, not in production, but threw it up there and started writing to it. Things looked all right. We did not have any maintenance put in place. This is a bad idea, we learned. Because we started to load test the hell out of it, we started seeing dropped mutation batches. We read up on that, and it was like, yeah, you should probably have maintenance in place to make sure that your consistency does happen in case there are drop messages in between your nodes. So we put maintenance in place, and all of a sudden we see a 2x growth in data on disk. We have no idea why. So we start, kind of getting concerned about that. We're looking into why it might be that our data has all of a sudden ballooned on disk, and we totally thought that if anything, it was going to shrink. So obviously, Cassandra is scalable, right? So we can just add more nodes. It's going to split the key space in half, and we'll have half the data on the disks, obviously. That's not really true either. We start seeing lots of data being streamed between the new nodes and the old nodes. We started seeing bootstrap failures due to load on the entire cluster. It wasn't really working out exactly as we planned. So started to panic and freak out. And so we moved beyond that, and we started to think about whether we had made the wrong choice. Was Cassandra really the right choice for our data store solutions? Should we have gone with a different technology? And the answer is no. We had made a good choice. We just had to fully understand what we were dealing with. So we started to turn to the community that was around us. Ask other companies in the area that we know use Cassandra. We have friends in the tech community, so talk to them. Had they seen these problems that we were having? Some of them had. We started talking to DataStax. We were getting a little bit of support from them. We started to really hammer them pretty hard with questions. We started to get ourselves into the IRC chat channels. Great place to get information. Talk to experts there and describe your problems and see if they've seen these before and if they might have answers for you or direct you in a good direction. So we took a step back and started to really analyze what was going on. We found out that your write pattern matters just as much as your read pattern. So, when we first started looking at Cassandra, we heard, design your data schema around how you're going to access it, right? It's not a relational database, and so, you want to be able to access it in sort of a predictable manner, and if you want that performance out of it, which was very important to us. But we found out later that your write pattern matters quite a bit due to your compaction strategy. We were using size-tiered compaction. It turns out that we were updating SS tables, or updating rows all across the cluster, or all across the key space on a regular basis. We actually, we knew we'd do a little bit of this updating, but we weren't quite sure how much of it we were doing. We did some analysis around that, and we found out that somewhere around 80% of our rows were being updated at a later time. It was a lot of them. And so if you've looked into how size-tiered compaction works, essentially as an SS table grows to a certain threshold, and there's another one at that threshold, it will compact the two of them into the next tier. And then once there are two SS tables at that tier, they get compacted into the next tier, and so on. And so you start ending up with these large SS tables of data that you wrote a little while ago, or hopefully a long while ago. If you continue to update them, you will start to see fragments of that row across several SS tables. And then when you need to reconcile that, just if you need to do a read, you might have to read from several SS tables. But if you need to stream that data, or if you want to do a compaction with size-tiered compaction, you need at least double or up to double your largest SS table on disk. If those are starting to get fairly large, you need quite a bit of scratch space. We learned that that was the problem we were seeing. When we put maintenance in place and a lot of compactions were taking place, our data was doubling on disk, essentially, because it was trying to reconcile all of it. There were updates all across it. And we found out it's extremely important how much data you store per node. When you do want to do growth of your cluster or any of these repairs or maintenance, the data that you have on one node is going to greatly affect the amount of time that it takes for that to happen, right? We were seeing when we put maintenance in place that it could be up to a week to do maintenance around the entire cluster, because we needed performance out of the cluster at all times, so we couldn't just take the whole cluster down to do repairs or anything like that. We wanted to do it one node at a time, go around the ring, and it could take up to a week to handle that. So the knobs that we realized we could start tuning there. One big one was, we learned with the compaction strategy that we were using what was going on. We decided not to go with a leveled compaction because we were worried that it would cause a low read throughput. If you're worried about that at all, it can put extra strain on your cluster. We decided not to go with it. Just understanding what was happening underneath was good enough for us. The compaction throughput, megabytes per second, was another knob that we realized could really speed things up for us. The compactions were taking quite a while. It's recommended that it be 16 to 32 times your write throughput. Out of the box, I think it's 16 megabytes per second, and we were seeing our writes at somewhere around like 8 megabits, or 8 megabytes a second. So we definitely had to up it. We upped it to, I think, 150, and we were able to see compactions were going smoothly. Our reads were not getting too greatly affected, and so we were happy with it. Made our cluster happy, and things were humming along. So later down the line, we came up with another use case for Cassandra. It was an n-day archive of Twitter data. So we literally were planning to throw the Twitter Firehose at it. And so, like I said, we regularly see about 5,000 to 7,000 messages a second in the Firehose, but we see these huge spikes up to 20,000 messages a second. So Cassandra was going to do a great job for us there. And so we decided, we came up with a schema. It was basically the tweet ID was going to be the row key, the column key is just a constant placeholder, and the value there is the entire payload of the tweet. We decided that we would do dynamic column families. So dynamic column families are just, create and expire column families as you go on. We bucketed them basically in 3-hour chunks, and we wouldn't use I forget what the term is, you can set a lifetime on your data in Cassandra, and basically it will handle removing that data at some point, but your storage reclamation might take some time. We would actually simply go ahead and just remove the column family, and then 3 hours later delete the data on disk. We have an XFS file system, so the deletes on disk are blazingly fast, and so things seem to be looking pretty good here. We weren't updating rows. 95% of our rows were written to once, and that was it. And we were going to be rolling these column families off, and so that would save us, essentially a constant amount of space taken up on disk. Our reads were going to be much lower than our writes. We're throwing the Firehose at it, but the usage, at the time of design was kind of undefined, but we were able to scale that. We knew it would be kind of one-off reads, user requested rather than anything streaming at it. So things are looking perfect for us. Everything looked fantastic, and we thought we had already been through the trenches with Cassandra, so clearly it was going to be rainbows and unicorns again for us, and not at all. We definitely ran into a couple more difficult situations. So a little bit about our current cluster that we have backing this product. We've got 16 nodes in the cluster, a replication factor of 3, each node holding about 2.5 terabytes of data. Trying to remember if that's including the replication factor or not. But we had 40 billion keys, which was an extremely important note that we hadn't really looked into. Because as we were growing it, like I said, it was an n-day archive, and at first, we scaled it up to 15 days, then to 20 days. Everything was looking fine, and then every time we'd try to get past 20 days, we'd start seeing GC thrashing. We were trying to figure out why, and so we started to look into the memory consumption aspects of Cassandra. And so I don't know if you guys were at the keynote speech earlier with when Jonathan spoke. He spoke directly to these actually being addressed in future versions of DataStax Cassandra. But there's a couple key components. When a read happens, it first checks a Bloom filter. And the Bloom filter is basically a piece in memory that will grow based on your data you have on disk. The partition key cache is a constant hold of a number or a size of keys that you'll have in memory. And then the partition index is also another piece of memory that will grow with your data on disk. We knew about our key cache and our row cache, and we were tuning those to appropriate degrees. But we really hadn't taken a look at the partition index and the Bloom filter very much. Specifically, the Bloom filter, we weren't very concerned about it. The Bloom filter, I think it's Bloom filter false positive chance is a setting, and I think out of the box it's like 0.0007% or something. And so, we hadn't really read into changing it, but it turns out with 40 billion keys, I think Jonathan actually had the stat earlier today. He said it was like 1 to 2 gigabytes per billion keys that you have is going to be taken up in memory. So 40 billion keys was a significant amount of memory we were holding up just over the Bloom filter. The index interval, the next one, is basically on startup, Cassandra will look through your keys and grab every nth key and pull that index into the SS table into memory. That way, when you go to do a read, it will basically say, okay, you're looking for key 10. I know where key 5 is in this SS table, so it can go seek directly there on disk and then start looking past there for your key. And so out of the box, I think that one's like 128. Every 128th key is brought up into memory. Again, 40 billion keys. We were looking at 315 million keys in memory. And so we bumped that up to every 512th key. Then we were down to 78 million. So it was a lot better on our memory. And with the Bloom filter, we brought that up to a 0.05% chance of a false positive, which is fine for us because we could, on the client side, determine whether or not it was looking like a valid key. We can determine if it's a well-formed tweet ID. We can determine if it's within our N days that we are currently holding in the cluster. And so there's only a couple of factors that could be in play that key is actually not going to exist in our cluster. So the Bloom filter false positive chance was very unimportant to us, except for the fact that it ballooned our RAM. And then the last piece was the compression offset. So that one is not really tunable that I'm aware of, but it will keep metadata in memory based on the number of keys that you have on disk. So it's just another one to be aware of, and sounds as though it's being worked on by DataStax. So the themes that came out of all of this were essentially, you're not always going to fit the mold. We definitely didn't in all of our cases. Our first use case of Cassandra, we learned that even though we thought it fit our problems perfectly, given our write pattern, updating rows all over the cluster, it wasn't a perfect use of it, and our read pattern was fairly intensive. We were throwing a lot of clients at it, and we thought it would scale out, which it has. It's definitely solved our problems after we were able to tune it enough. But you're not always going to fit the perfect description of how Cassandra should be used. But if you learn how it works underneath the covers and you use the 400 configuration options it has to tune it to exactly your use case, you can really get a lot of horsepower out of it. And so explore those options. There's that huge configuration file. There's a lot of startup options for Cassandra. You can set a lot of properties for your column families as you create them. So after we figured out what those settings really meant and what we could do with them, we were able to leverage the power of Cassandra more than we ever thought. Understand the consequences of your choices. When we decided to just start running repairs and throw new nodes at the cluster, we didn't quite understand why it was trying to stream almost all the data from the first node when we thought it was splitting the key space. Then it turns out it was just trying to reconcile the data after it computed the Merkle tree. We didn't really realize why, though. Another big one that we hit was keep your staging environment and your production environment identical if it's possible. There's a lot of things that you might not think matter. You might think if I have half the nodes and I keep just half the data, then my production environment, I should see the same things happen at the same times. And that's not always the case. Keeping the staging environment and the production environment identical will help you to run stress tests that will exactly mimic what you'll see in your production environment when your customer or your publisher or something like that stress tests your system one day. And so that kind of wraps it up. If we have any questions, I can answer them. I don't know. No? All right. Well, my name's Andrew. I'm with Gnip. You can tweet at me at Noonanisms, or Noonisms. And thank you.